Nice to have you all here. Today we will start with the first webinar of our workshop series about engineering simulation for drones. Before we actually start and dive into this very spectacular topic, I would like to know if everything is working from a technical point of view. So this webinar is broadcast and hosted by GoToWebinar, which is a software you all are using right now to listen to my presentation. And maybe just everyone who can hear me, could you please raise his hand? There is a button on this control panel you have where you can raise your hand just to show me that you can hear me and everything is fine. Great, I can see a lot of hands rising up. Therefore, I think it's working for most of you. If you have any some technical problems, please use the chat to write me a message and we will try to solve it. Most of the times there are some problems with audio, which is or the reason for this can be a driver problem if you're using Linux. In this case, you can try to dial in with the toll-free number we are providing, or in the worst case, we will also upload the recording of this webinar so you can watch it again if something is not working right now. Great, then let's start. Yes, and maybe let's first take a look together at the agenda of our workshop series and let's discuss just what the aim is. We want to show you different aspects of engineering simulation, how they can be used to design and optimize a drone, a quadcopter, whatever related to this. We will have 4 sessions, one about aerodynamics and fluids flow simulations, and 3 about structural mechanic optimization problems. Like, for example, optimizing the topology of a part to make it reduce the weight, or we will also do some kind of crash testing and analyze the vibrations of a drone chassis. So there are a lot of different aspects which we will work on, and the idea here is that in every webinar session we will give you a short introduction to some physical background stuff, show you how to set up a simulation, and you can for sure ask all your questions. And all of you are provided with a free premium access to SimScale for the next 6 weeks. So then you can later on use our homework assignments, which we also provide, to apply the knowledge you gained. And for everyone who will submit all homework assignments, we will award him with a free professional training, which has a value of 500 euros. Well, so let's get started. The agenda today is we will start with some basic know-how about aerodynamics of drones. So we'll talk about actually how a propeller is working, what where aerodynamic is important and where not of a drone, and yes, how you can use aerodynamic to optimize your drone. Then we will together set up a simulation using SimScale of a drone, aerodynamic simulation, doing some result interpretation together, and then I will present the homework assignment to you, and there will be some time for question and answers. Maybe just to introduce myself. My name is Milad. I'm working here at SimScale as academic program manager. So I'm responsible for all the stuff we are providing for academics, like we have our academic program, which gives free access to students and teachers, or for example, this workshop series, which is also part of the academic program. I've studied mechanical engineering, so I have a classical engineering background, and I got in touch very early with simulation, and so therefore I'm very excited to work here at SimScale and hope to bring the simulation technology to the desk of all engineers in the future. Again, this is maybe very important because some people also sent me email with questions in this direction. This workshop is really about to get some first interesting insights about the application of simulation in drone design, and we also want to give you some first experience which are very hands-on how to use simulation, so that after this webinar hopefully you are able to optimize your own drone designs using simulation and SimScale. Nevertheless, this is in the end for our webinar, if you would add all the single webinars together. Therefore, we cannot deliver everything. This is not a lesson, lecture, or training about simulation theory. If you're really interested in the fundamentals of simulation theory, there are a lot of good books. Also, you can check out our blogs. And if you're studying engineering, something like that, I'm quite sure there are some interesting lectures which will give you a good insight. And in the end, this is also, let's say, not a complete fundamental training. So if you really want to use SimScale in a larger way for commercial applications in a company, I would recommend to check out our tutorials more in detail, and we also offer this professional training I mentioned, which you all can win or which you all can qualify for, which also for companies. So if you want to really use it in your company. Yes, we are really, this is not our first workshop. We had a workshop half year ago, for example, with a very famous guest speaker about simulation Formula One car design, and we're doing this because we truly believe that simulation should not be limited anymore to big companies who directly dive into our hands-on demonstration. As I mentioned, these are 4 1-hour online sessions with a homework assignment. And yes, we will later on talk more detail about the homework, but you can share it with us if you want to qualify the training. Maybe let's just discuss about the 6 questions which were asked several times. First of all, will this workshop be recorded? Yes, every session will be recorded, and you can access it latest 1 day after the session. So tomorrow, I would say around 10-11 a.m. you can on our website simscale.com/drones access the record. A lot of people ask if they should start to set up simulation parallel, and I would say absolutely no. I think it's better really to listen first. You have the record later on, and we will provide you with hands-on step-by-step tutorial. So it absolutely makes no sense to start to simulate during the session. If you all of you have already a SimScale account, so if you want to know how you can simulate yourself, this is exactly the right session for you, the right webinar. And you can, yes, as I mentioned, hand in your homework using our homework sharing form, which I will present later on. What if I have trouble setting up my simulation? That is a question which was asked a lot of times, and the question answer is here: use our forum. Our engineers will really provide support, so if you have a problem with simulation setup, just go on our forum. It's, as I mentioned, forum.simscale.com. Log in there with your SimScale login credentials, and there we have a special category, workshops and webinars, with a subcategory drone workshop. And here, for example, you can already find the step-by-step tutorial for the homework assignment. There's a topic just about questions which was already used by you. So if you have a general question, put it here. And if you have a question related to one of the homeworks, just write it as a comment in this forum topic, and our team or maybe some of you guys will answer and help you. Okay, then let's get started. And yes, before we start the simulation, let's talk a little bit about some physical fundamentals. I mean, there are a lot of kind of different drones, but let's say most of the drones, or all drones I know, in the end are working somehow with a propeller to fly. And here the question is, how are they flying? Maybe some of you already know it. For those who don't know how a wing is working or how a plane is working in general, the idea of a wing is that you have two sides, two shapes of the wing with different length. And now the idea is, just imagine, from the right side is flow streaming to the left side. And then there is a wing, so the flow has to stream around this wing. And now the upper side, this is shorter than this lower face, this lower surface. And the air cannot be destroyed here. So therefore all the air coming in on the right side must also leave this, let's say, area on the left side. And if they have different lengths, that means that the flow on the underside of the wing has to be accelerated. It must be faster, otherwise it would not work. You know, because the flow is coming together here, it's split it up, and if it should meet again here, then the flow on the lower side must be accelerated. And for this acceleration, you need energy to accelerate something. It's the same for flow. And you know energy cannot come from nowhere. And in this case, the energy needed to accelerate the flow is taken from pressure, so the pressure is reduced. And that will lead to a suction effect. That means I have a pressure difference between the upper side and the lower side, so the high pressure is green, the low pressure is yellow. And this results in an overall force which is acting on this wing. In this case, this is let's say a car wing, so for an airplane would be another way around, because now the wing is pressed down, but that's actually how a wing is working. Okay, and this is, as I mentioned, a very simplified example for two-dimensional shape. In reality, if you have a quadcopter or a helicopter, or you know how the way most of the drones are designed, you have not a wing, you have a propeller. And the difference between a wing and a propeller is that a wing, you know, is float translational, but propeller, it's rotating, and that's the way the air is streaming around the surface. So I have a rotational component in the free stream velocity, and that leads to something else. If you just go back here, we have a uniform let's say inlet flow velocity here. For propeller with this rotating, this is not any more uniform, because I have a rotational speed here in the rotational axis of the propeller, and as more far I go away from this axis, the speed, actually the speed on the surface of the wing is also increasing. You know, because it's the same like if you because it's rotating still with the same frequency, but the length of the of a circle, which we would just imagine we just have a circle here around, would be longer. And that means, and that about let's me other way. That's the reason why a propeller is not looking like a wing. Why it has this dynamical shape, which is let's say really three-dimensional. We have a changing cross-profile section, and it's a little bit twisted. And that's because of the reason that you have different flow velocities here, and therefore you have to optimize, let's say, the wing at every point here. And so in the end, the way a propeller is working is that you rotate this the propeller. That leads, you can see it here in this lower sketch. This is in the end, let's say, the wing. Again, to this effect that this side, the upper side in this case, is longer. Therefore, the flow is accelerated. The pressure is dropping. And then this is a pressure difference here, which creates a force which we call lift. Or to be more concrete, it's not only lift. The lift is then you can have two components of the lift. One is the thrust in the end, which is accelerating an airplane, or which is the reason why we can fly with a quadcopter, and the other thing is something like a drag. So it's a torque you need to accelerate the propeller. Yes, and that's basically how a drone is working. And what we will do now is, you maybe saw on our website this design, this quadcopter. This quadcopter is or was designed by one of our users, Asen. He's a very smart guy. He is a student from the US. It's not his first drone he designed, and it's somehow modified for us. So it's a SimScale drone. You can also download it, all the CAD files, including a bill of materials, and build this drone yourself. On our website there is a link. And what we will do now, Asen used a standard profile, a standard propeller profile, which is good. And we will try right now to optimize the shape of this profile with the help of simulation, so that we have a higher lift force with the same engine, and that will allow us, for example, to make the drone bigger, or make it in the end to transport a higher weight, because we have a higher force which can be used. And there are basically 3 steps if you want to do engineering simulation with SimScale. First of all, you need a CAD model. You can use any CAD application you want. We also have a partner company called Onshape. They are doing CAD in the browser. You know, we're doing simulation in the browser. They do CAD on the browser. So if you don't have access to any CAD system, you can for sure also use Onshape. And when you've done the CAD design, you can upload your CAD model. By the way, we're supporting several file formats to the SimScale platform. In general, it's necessary to prepare a CAD model a little bit for a simulation, and it's very easy to understand why. For example, let's take another example. Let's take an airplane instead of a drone. If you would upload the CAD model, including the thousands of screws, it wouldn't make the computational effort of the simulation thousands, millions of times bigger than with a simplified model without the screws, but it would not add really a value, because the influence of the screws on the aerodynamic of the airplane is, compared to the whole aircraft, it's really not significant. And when you've uploaded your CAD model and simplified in the best case before, then you do something we call meshing. I will just explain in the next minute what meshing means. Do the simulation setup, and then you get a result, and you can use this result to make it, for example, a design decision, or to improve your design with a continuous testing procedure. And before we start to set up the simulation together, let's just shortly together discuss, because this is very important, what is the physical meaning of our simulation. As I mentioned, this is very important because you can only simulate in the end what you know. And in this case, we will use this quadcopter of Essen, and only use a quarter because it's symmetric, and make a fluid flow simulation. So we will simulate the aerodynamic. And this is, by the way, a cut model of the later simulation domain. And here you can see in green the surface of the quadcopter, and then this outer box. The outer box we need later on as a, let's say, flow domain, which we want to investigate. And we will use later on some kinds of boundary conditions. So to make this realistic, we have to play a little bit around. First of all, this, let's say, I think it's for me it's yellow, but it's maybe orange. Yellow, this yellow faces here and here, they are symmetry planes. The green surface, it's a physical wall. We call it physical wall. So it's a real existing wall, in this case of the propeller, which will interact with the air. And the blue one, this is a little bit tricky to understand, but I think let's try it. In reality, there are no walls. If your drone is flying, you know, outside, there are no walls. Maybe the floor, but not on the right, the left, the top of the drone. But we have to limit, in the end, we have to limit the computational domain, because, you know, computers has a not an unlimited capacity of memory. And therefore we design this box, and all these blue faces will get a special kind of let me call it boundary condition, which helps us to avoid this effect that there are walls. Okay, and now let's start. We will go on simscale.com, and here you just log in with your user account, your password. And yes, I've already prepared some stuff. So here we have a project where I've uploaded both the initial design of the blade, which you can see here, and our modified design. You see the differences, that this is another angle of attack, this one, and the shape is a little bit different. You can also upload your own geometry, you know, just using this upload geometry button, select the file format, browse for a CAD file, and start the upload. In this case, we also did something more. This CAD models not only include the geometry of the drone, they also include, you can see a cylindrical geometry around the propeller. We've created this geometry in the CAD application because we'll need it later on. Because we will use this region to define the rotation, the physical rotation of the air. So for simulations where you have rotation, you have to create this kind of rotation zones before in your CAD model. And we will now together do all the steps. So we will create a mesh. A mesh, to understand what mesh means, is you have just to figure out, you cannot calculate later on for all points in your computational domain the physical quantities like pressure, velocity, etc. That's not possible because, as I mentioned, the memory of a computer is limited. Therefore, what you will do, we have to tell in the end the computer, or in this case SimScale, where do I want to have a high precision and where do I not need a high precision in the simulation. And so we are telling the computer exactly at which point of this domain he should calculate. You can really compare it like a digital image. It's like, let's say, the simulation pixels in 3-dimensional, and there where you have not expecting a lot of changes, like outside, far away, you can make a coarser, bigger pixels, and in the near of the propeller, for example, we will have a lot of changes in the air field, the flow field. There we need some finer mesh, some finer pixels, let's say. And this process is called meshing. This is the first thing you have to do for a simulation. And this is exactly what we will start now. We go to our project again, mesh creator, and then we click on, this is the project tree, by the way, so your simulation will be somehow built up here like a tree. And this tree will also guide us through the next steps. What to do first is we will create a new mesh, clicking the button, call it Drone 1, for example, and now we have to select which CAD model we will use as a base for or which CAD model we will mesh in the end. And I will select Drone 1, confirm it here, and then you can see that the CAD model is now added to this mesh operation and we can start to create our mesh. Next thing is to choose a mesh operation. So we first define what we want to mesh. Now we have to define how we want to mesh it. And here you have a lot of different options. In our case, because to be honest, this is not a beginner simulation, it's rotational parts, it's really something advanced. We cannot use one of the automatic meshing tools for simpler simulation. We have to use, or will use, SnappyXmesh. SnappyXmesh is an open source meshing tool, which is, by the way, also used in Formula One, in research, in aerospace industry. And we will use it now to create the mesh. So we select it here, save it. This is very important. You have to confirm everything you do with save. And by the way, because we're working on the web browser, it cannot crash, and even if your computer would crash, everything you do is saved in real time on our servers in the cloud, so you can never lose any kind of data. Now, yes, you can see when we press the save button, some items were added to our project tree. This one, first of all, is a base mesh box. This is in the end the domain. So now we will define this domain around our drone, and you can specify this domain with two opposite points of this cube. And yes, let me just type in the coordinates, which I prepared this for sure. What I would, by the way, if you want to do simulation yourself, what I am doing here is I'm using in my CAD model, creating this box first, and then I can extract these points from a CAD model. And now you can see this is our box, which we will use now for the simulation. This is a little bit bigger than on the slide, because we want really to avoid interactions between the flow and this wall. Okay, confirm with save. And then the next thing we have to define is the so-called material point, because what this SnappyXmesh will do is now to fill out the area between the drone and this cube. And so you have to define here a point which should be in the mesh. And yes, one point which is definitely in the mesh is this one. And here, by the way, you can hide and show objects, and you can see that this point, this is our material point, it's in the right place. Okay, and yes, now we can start, basically. And first thing we will do is, if you look again here, we will define so-called base bounding box mesh size. So we have to define how big should be the elements, the mesh here, because the wasteland packs is working with a base mesh size, and then you're adding local refinement, and so that's the largest mesh size we will use. And in this case, we will use 30 elements for an x direction, so on this for this edge, 40 elements because it's a little bit higher in this direction, and again 30 elements in this direction. And we will use 16 processors, which will accelerate. Yes, it will accelerate the time we need to create this mesh. Okay, then there are some additional settings we have to change here. These are not necessary basically, but we will just do it to increase the mesh quality, just so, and to make it faster. And these are here. So, by the way, you don't have to note everything. We will later on just provide you with all the values for the homework assignment. These are some special value optimized for small geometries. If you want to know exactly what that means, it's not necessary, by the way, because we provide you with different settings, also in documentation. But if you want to know exactly what it means, you can check out also our documentation. Okay. That is it. And now we can start to create the mesh. There's just one thing missing. We want to create an additional refinement zone around the drone. Yes, so you'll again enter the points. And now we have an additional refinement zone where we can refine the mesh and the elements. And now we are nearly finished. Now we are really at the point where we're defining the actual refinement. First of all, as I mentioned, we have this zone, this volume, the cylindrical volume, which we will later on use to define the rotation of the air, because the air is rotating around the propeller, and this has to be defined in the simulation manually. So we'll call this rotation. Choose as a type surface refinement, and here is the option create cell zone true. This one is solid 1, select it here, and we define a refinement level. By the way, this will also explain what refinement level means. What this base mesh size we defined before is refinement level 0. For each additional refinement level, the cells are splitted. So level 1 is half the size of level 0, level 2 is half the size of level 1, and a quarter of the size of level 0, and so as higher this number is, as finer is the mesh actually. And here let's call it rotator. So that's the name for the latest cell zone, and now it's applied. Now we have to refine some of the surfaces. Therefore, let's hide all the boxes here and also hide this, and let's start with the refinement. By the way, you can interact with the model, as you know, with your mouse, and if you want to change the center of rotation, just double click with the left mouse and then you can change it. And here, for example, you can, if it's necessary, reset the view. Okay, now in here you have to be very careful. It's really to select what you need. So this is done. Let's call it surface refinement. Choose again the type surface refinement. Now we add a refinement level, and we can add the selection. Oh, this was wrong. Now we can add the selection, which is red here, as a refinement. Yes, and then we will just create 2 more refinements, a region refinement. So we will refine everything inside this Cartesian box we defined before. Define a refinement for the blades again. This is again a surface refinement. So select the blades here. And here you have to be careful. Yeah, there's some small faces. Add it and make this region very fine, because here we expect the most changes in the flow field. Nice. Now the last refinement, it's a little bit here to explain it. It's called layer addition, and that means layers are a special kind of mesh, which is very good for solving turbulence and aerodynamical effects on surfaces. Therefore, we'll assign it. So it's not a refinement, it's more a special kind of mesh. We will assign it to the whole drone, including the blades of the propeller. Yes, and now we are done. We can just start the meshing here. And now our mesh will be computed. And exactly the same way you can create the mesh for the second drone. But this can take some time, up to 10 minutes, 20 minutes, because it depends on the mesh size. Therefore, I've prepared for sure a mesh we can use. But just as a wrap up, what we've learned: how to upload a CAD model, what hex dominant meshing is, and let's say, brief overview about manual meshing in cell zones. There are a lot of other stuff we have not mentioned here in this section. It's CAD cleaning. I think I just talked a little bit about it, but didn't show you how to do it. We didn't. There's some other additions or advanced topics like mesh quality assessment, more manual refinement option with the existing, and porous zone, some additional kind of mesh zones. Great. So now let's start with the simulation setup. So we have now our mesh, and now we can create our simulation. So click on, we switch to the simulation designer tab. In this project I prepared the mesh, so it's the same mesh, but add new simulation, and then you can choose which kind of simulation you want to run. And we want to run incompressible fluid flow simulation. Incompressible means that we are not expecting airflow velocities in the near of speed of sound at the end. And then here you have to choose between a turbulence model. And turbulence model means it's a special way to calculate, vortexes and turbulence or flow. This is very complex, and without the turbulence model, it would be too much computational power necessary. But using a turbulence model makes this easier. We use K omega SST, which is a standard turbulence model for automotive industry. Steady state. Through steady state option, it means that we're only interested in a static solution. We're not interested in what happens before or after. We just want to know what is happening in average with the flow. Then save, and that will create a new project tree for your simulation. First of all, on the domain, you have to choose the mesh you want to use. In our case, drone mesh. Drone mesh. And here you can see how the mesh is looking, by the way. So this is. We can, for example, now hide the surfaces and take a look inside. And here now we have, by the way, our two mesh zones. This is for rotation, this part, and this is the rest of the mesh. And here you can see how this surface refinement works. We have here this level 7, so it's very fine here. And in general, this is the box we created before, this refinement region box, and then you have automatic change of refinement to have an optimal mesh quality. And now what we have to do basically is to define initial and boundary conditions. The meaning of this is very easy. A simulation application works the way it's that you have an initial solution, and this initial solution is iterated again and again to increase the accuracy of the solution. And so you need a start value, a start simulation result. And this one is defined here. In most of the case, it's not necessary to touch this value. So here, for example, pressure, velocity, K and are 0. So in the whole simulation, the first step, and K and omega are also uniform everywhere. This values are standard values. You don't have to change them. And based on this, the simulation will start. So we will not touch it. It's fine. The same for model, where we can define which kind of fluid we have, in this case air. Now we will start to define the boundary condition. This is something different. The boundary condition, let's say, are used to describe how your model or how our drone is interacting with the environment. So we discussed it before. We will start with these two faces, which are symmetry. So you have to assign at least to every face exactly one boundary condition at minimum. And let's start with these two faces. They are symmetric, so we use the type symmetry, call it symmetry, and then we can, like the meshing, select them, and with this add select from viewer button, assign them. Then we go again on this entry in the tree, add a new boundary condition. Let's call it slip, because this walls, the other walls of the box, will be so-called slip walls, so there is no friction and therefore no interaction between the flow and these walls. Be sure or not to select again these two walls. That would also give you an error message. Here we choose wall, slip. This wall treatment, you can't don't have to touch it. Again, add from select from viewer, and it's done. Last but not least, we have to define the boundary condition of the drone, of the surface of the body you want to investigate with the simulation. And here a trick is hide all the outer surfaces. This one also hide. And now we'll select all. We can select this option. Select all selects all visible surfaces. So everything is selected. Write a new boundary condition. Select all. Call it drone. A wall, but in this case a no slip wall. Add select from viewer, save, and it's done. Last but not least, we are adding the rotation to the simulation. So you can find some advanced concept, rotating zones, and then we have to just enter the center of rotation. This can be found out in your CAD application. In this case, I've done this for sure before. And the rotation axis, which is in y direction. And following the right-hand rule, maybe some of you know, we now have to enter the angular velocity. And this is in our case 2100 radians per second, which is about 20,000 RPM. And now choose the mesh zone we want to apply, in this case rotation. Nice, now the simulation setup is basically done. What we can do now is play a little bit with numerics. Numerics are, let's say, some settings you can use to make the simulation faster. So this is something you need experience for. Here we have some standard values. And what we will do here now is use smooth solvers instead of the standard solvers for velocity, K and omega, and a GAMP solver for pressure. This is numerically more stable. You should keep in mind that in the end, all we're doing here is really high-level mathematics in the end, and therefore there's some stuff you just have to know. But all this information we provide you with in our documentation, and also for the homework assignment, we provide you with very nice step-by-step introductions, including some explanations. Okay, save here. Now we have to define how long the simulation should go, because as I mentioned, it's an iterative simulation approach. So as more iterations you're running, as more accurate should your result become in general. In this case, we will make 3000 iterations. So starting from 0 to 3000 with a length of 1. And we can write out some interval results, which is in this case not necessary. You could only do it, for example, if you have a transient simulation, or if you're interested in the results, not, let's say, ready results, then we have to choose a number of processors. And this maximum runtime, this is a kind of protection for our users. So if you would be a commercial customer and you would be afraid of burning your core hours because of some wrong settings, you can just limit the time the simulation can run. So this is real time. 3000 minutes is less than 1 hour. So to be safe, let's make it 18,000 seconds, would be 3 hours, but I don't think that we will need so much time. Just save. And now, because if you think back, why are we doing this simulation? We want to know which propeller design is creating more lift. We can create an option, or we can create a so-called result control items, which will calculate the force for us, the lift force. So here add force, type force, and moments. Let's call it force. Then you need the density of the air, of the gas, and density of air is 1.205, and the center of rotation. Here will we use just, this is the gravity center, the same center like for the MRF zone. But by the way, for the force, that makes no difference. This is just important if you want to take a look at the moments. And now again, we have to select all the surfaces here we want to be investigated, added here. Now we are done. The simulation is completely defined. And we can start now to run it. So create a new run, start, and now a simulation is running. And by the way, our mesh operation is now also finished. And let's now just take a look at the results I've prepared it. So I've also prepared the second mesh of the alternative design, set up the simulation the same way, and then we can take here at post processor a look at the results. So first of all, you have this mesh, this tree again. These are the two simulations, and the first thing we'll look at is the so-called convergence plot. So the convergence plot shows the accuracy of the simulation. This is the number of iterations. This is, let's say, the error. And you can see that the error for all physical quantities is decreased with the number of iterations. And in the end, it's very small. So the error is, this is the error here, the number here. So it's very, very small. And that's a good sign. The team-out simulation has to be worked. And then we're going to take a look at the forces we measured. And this is, in this case, the green line. The force, the pressure force, this is lift in y direction. And here you can see how it became more accurate with the iterations, and now it's somehow converged, so the value is not changing really anymore. And here we have 2.16 Newton for the initial design. And if we take a look at the another design, we have with the same boundary conditions a force of 3.42 Newton, which is 60–70% more lift. And yes, so just what we've learned here, how to set up a simulation. So we talked about simulation setup, initial condition, boundary conditions, how to create a rotating zone and how to start the simulation. And this knowledge is enough really to simulate, let's say, all aerodynamics for drone designers. There is some advanced topic you could do, like porous zones, if you want to have, or some reason I don't know, for example, a heat exchanger or some cooling there. And what also we would say is advanced is if you would talk more about numerical solver settings and about this transient dynamic simulation setup. Well, next step, in the end we already started with it, is so-called post-processing, so the result visualization. First thing we've done is, yes, we have just compared the forces, and if you also want to understand why the force is different, you can make 3D visualization of the results. You can do it directly in SimScale, here clicking on solution fields, for example. And then you could here do some visualization stuff here. But in general, because you can see this also with this beta tech, we would recommend to do it locally on your own computer because that's more comfortable at the moment. But we will have soon the new version of the post processor, which will be even more faster and better. And for this, we recommend ParaView. It has exactly the same tool in the end we are using here. In SimScale Online, it's a tool you can download for free. Just click this button here. It's an open source tool, yes, and then you can do post-processing there. And just to show what you can do, for example, here is you could, for example, now create a slice. In Y direction, let's say. And now, for example, if we take a look, you can see the velocity field here. But let's do it locally. I've already downloaded the results, so we will start ParaView now. If you want to download the results for local post-processing, just go on the simulation one, then you can download them here. You have just to extract the archive and then you can use it. And we will now just open both simulations. First of all, we have to extract it here. Then just open this case.foam, read in all mesh arrays. And then we can do some result post-processing here. So I will do it now quite fast, but don't be afraid. You will get for this also some online tutorials on our website, and for sure this is recorded. So what I will do now is just jump to the latest iteration, so to the most accurate state of the simulation. And then, for example, I will extract all faces expect the bounding box, so this is the surface of the drone for the initial design. And for example, now you can take a look at the pressure distribution, and if we play a little bit around with the range, you can really see how it's working. We have the suction side here, the higher pressure here, and that's the way how the lift is created. You can also do, for example, a cut through the field, through the flow domain. And then here, for example, we can take a look at the flow velocity. And here you can really see how the propeller is working. So that here is air, red means high value, is streaming up. And this upstreaming air is accelerated by the propeller, and this creates a lift. And I mean, there's nearly unlimited possibilities visualization. Maybe one last thing I want to show you is our streamlines. Here is the seed point where we want to start to seed the streamlines. And I will just take it, put it here. And then we also have streamlines. Okay, but I've prepared some screenshots so that we don't have to post everything right now. And here you can see, here's the upper image is the initial design, the lower is the redesign. Here you can really see, first of all, the difference in the force. So we have here so much more lift. And you have, I mean, in the end, 2.16 Newton, we have to multiply with 4 for the full model, would be, let's say, 9 Newton. It's even less than 9 Newton. And 9 Newton is around 900 or 0.8, 0.9 kilograms. But with the new design, we have more than 12 Newton. That's nearly 14 Newton. So we can carry in the end 400 to 500 grams more weight with the same drone, just by redesigning the propeller. And you can really see here on the pressure distribution that we have a much bigger area which is blue, so a much bigger suction on the propeller. Then here we have again the pressure distribution on the drone, and then the velocity magnitude in the plane around below the propeller, and you can really see that here you have much more flow streaming through. So if you would like now to optimize the wing, what you could do is, instead of just taking a look at the forces, try to change the shape in a way that would make this area, red area, bigger. And here it becomes really obvious. This is the velocity again. In this case, it's a cut through the profile at the same place. And you can really see that this lower design is so much more accelerating the flow, and that's, by the way, the reason why we have this higher suction. And last but not least, the streamlines, and here again you can see that the new design, it's sucking such a lot of more air from a wider range of the flow domain, so it's using more of the air, and that's also another reason why it's performing better. Yes, then I would say, are there any questions regarding simulation design or something like this, someone? If in the case you have questions, please just type them into the chat here. Okay guys, then let's do the next step. Let's talk about your homework, because I know it was now a lot of stuff you had to learn, and the most important thing is that you can apply the gained knowledge. So we have prepared a homework for you. You can access this homework on the SimScale website. Here, simscale.com/drones. And now you maybe notice that we have, it's still, let's refresh the page. And here now we've added a new section where you can access, for example, the homework assignments. Well, let's first discuss about them. So what is our assignment? You have 2 levels for this homework, and don't forget, we have provided you with a step-by-step instructions, and who is submitting all homework assignments will get a free training. So the first level is quite easy. Your job is to investigate the following. Just imagine you want to design a new drone, and then it's not enough just to know the force for one rotational speed. Then you would need a kind of characteristic curve. And we want now to know how is the curve, how is the lift changing with rotational speed of the propeller. And you have to find this out for both for 2 designs. Therefore, we will provide you with a public project where the mesh is already existing. So the only thing you have to do is the simulation setup. And we will provide you for this also with a step-by-step tutorial, which you can find here. Here, again, we'll explain everything. So what really the exercises. Yes, and this everybody should be able to do the homework with the help of this, and then just follow this instructions. You can import the homework to your workspace by clicking here on that link. It will, maybe we can just show it. Import the project here into your workspace with the mesh and the geometries, or you can also import it directly from this main page. Well, and then you have in the end to set up the simulation for each propeller, 4 different simulations, at least 8 simulations. But the good thing is once you have set up the simulation, you can just with one click change rotational speed. And then when you're done, you just have to share the project with us. So when you finish the work, you can create here a public project link. That is the way you have to submit all the homework. Just copy this link, and then here on our website we have a form where you can submit the link of your homework. Please write the same email address here used for the platform, and then we will review your homework and give you feedback. And the next level, or the next, is a little bit more difficult. It's just one simulation, but here we want to investigate what happens if we use or put a ring around the propeller. And here we will provide you only with the geometry, so you have to create the mesh yourself, but I think I just showed you how that will work, and set up the simulation yourself for 20,000 RPM. But again, here we have a step-by-step tutorial guide, which you can also find here on our website. And yet everything is in the forum, so whenever you have a question or you don't need help with tutorials or with the homeworks, just log in, SimScale account, and write a reply in this topic. Yes, I hope you all enjoyed our first webinar. It was a great pleasure to work with you here. Sorry again for some of the technical issues we had. And now is yes, if you have any questions, that's the right time. Just raise your hand or write it into the chat if you have a question. Oh, sorry guys. Yeah, a lot of questions. I hope enough time. Let's start. Okay. First question is by Tazo. Tazo wants to know what ratio we recommend in terms of domain size to proper diameter for accurate results. Just a second. Okay. First question. It depends on the application. In our case, let me get into the simulation. I would recommend at least to have a ratio of, let's say, 1 to 10, and to the sides, and maybe in y direction it should also be minimum 1 to 5. And there's a second question also. What was the mesh count in the simulation? You can see the mesh count just here, 1.3 million elements. This is quite not a lot, so we could even make use of finer mesh. Okay. Prabhu asked, what is the reason for using a material point? Okay, then I will just talk again about this. We have the geometry, Prabhu, and we have the bounding box. And the meshing tool does not know where is the area between it, so you have to specify it. So because there are two possibilities, you could also, because this box is a kind of volume, you could also mesh inside of the geometry. And with the material point, you define in the end where's the outside of the geometry, and where the material point is, there will be the mesh created. Did that answer your question, Prabhu? Okay, great. Then next question is, why is the air from the propeller recirculating the computational box? Should the air come in the bottom and leave the top of the box? By the question by Christopher. Christopher, this is a good question. In the end, when we're talking about simulation, it's every time it's about simplification and associations. In this case, we decided we know that the influence, because the box is so big, will not be so much negative on the result, and it's better or easier to set it up this way that the air is circulating here. And that was, by the way, the reason why we use this slip wall boundary condition for this and for this wall, and for the outer walls, so that this has to minimize this effect. But you're right, basically it's also possible to have air which would leave and come into the box, and that is exactly what you will do in the homework number 2. Cedric wants to know where you can see the theory about SimScale algorithms. You mean about the codes we're using? For this, just check out our website, and there on the resources documentation, you can find information about our solvers in general, for example, about the validation of our solvers, or on the resources, we also have an overview of the solvers we're using. Sri wants to know when the video will be available. It will be available tomorrow in the morning. And Emmanuel asked, can I simulate various RPMs for various geometries? Yes, you can, and that's exactly what your homework is. So just check out the homework. And CDART want to know, or he wants to perform a mesh refinement study, which is quite advanced. So he wants to investigate how big the influence of the mesh size is on the results. And yes, you can do it. And you want what initial mesh size you should use. That for sure again depends on the model. But in this case, I would say if you want to do it on the drone model, you can make it a little bit coarser, so reduce for the, let's say, start model, all the refinement levels by 1, and then you can increase it a little bit to have different meshes. Are there any more questions? Oh, yes. Okay, 2 questions. Tazo, you want to know if you can import a mesh to a simulation. Yes, that's possible. You can import a mesh or different mesh formats here. So you can choose between OpenFOAM, UNV, and EGC. And so if you want to use for something else, the external meshing tool, that's possible. For the homework, you have to use SimScale, by the way, also the mesher. And Carlos wants to know when he has, how much time he has to upload the homework 1 week from now. So the next 7 days, you can upload, do your homework and submit the link. Just the link, please, because you was talking about uploading. And yes, then we will close this form and open a new one for the next workshop session. Emanuele, wrote something about the RPM of the propeller stall. You want to investigate the stall, right? So when the flow is separating from the propeller. That is a good question. What I would start then is, what I would do is really start with low RPM, like 1000. And then, make it higher till you see a first big separation, and then to look in the range between them. Or what you can do for sure also, there are some formulas like the Reynolds number, which you can use to calculate a rough, or to get a rough idea when the flow will separate. Therefore, maybe you should just, or write me an email if you need some more help. I think this is something very specific. Right, guys, I seem there are no more questions. Then I would like to say thank you again to all of you. It was really nice to have you here. I really liked your questions. I really hope to see a lot of homework of you. If you have questions, use our forum. And yes, so I'm looking forward to see you next week. And yes, have a nice day. See you soon. Bye.